There we go. She's level. We nailed it. Hello everyone and welcome back to Abbe Unlimited. We're going to continue our machine alignment and maintenance series. Please refer back to the introduction video to see all the steps that are involved in machine alignment, and we'll talk about some of the nuances ahead of time. So this segment is going to be specifically on leveling a machine. The very first thing that you must do with any machine when you bring it into your building is level it. If you skip this step, everything that you do will have error in it. The machines must be level. If you've ever walked across an overpass or a bridge and had a big truck drive over the bridge moves. It's a very large, strong structure, but it moves. Your machine is just like that bridge. It's very large, it's very heavy, it's 1-inch thick plate in some places, but it's going to move. And if you want to hold tolerances in the thousandths of an inch or less, you have to have that machine level. So when we level a machine, what are we looking for? Well, first thing we need is a level. Let's go get a level. I got my level. No, you don't. I wouldn't build a house with this level. Maybe a shed. Okay, maybe hang a bookcase. As we talked in video 1 in our introduction, you have to use tools that are accurate enough to get the accuracy out of the machine that you're expecting. You need to have tools that are more accurate. We talked about wanting at least a 4 times ratio between the accuracy we want and the tools we use to get it. Preferably, we want 10 to 1. A carpenter's level is not going to level the machine. This is made for wood. The dimensions of wood change depending on the time of day. So we cannot use a carpenter's level. So what kind of levels are we going to use? We're going to use high accuracy machining levels. Now the difference between this level and a carpenter's level is first the base and the structure of it. This is a very heavy steel base, and it's precision ground. The next thing that's a big difference is how they form the level tube. So this glass tube is going to have a much larger radius to it than a carpenter's level. So the glass tube actually has a small radius in it, and that's how the bubble forms and stays in the center. If you notice on these levels, the bubble is much wider, and the reason for that is because of the very large radius of the tube. It also makes these levels extremely accurate. So this level that I'm holding here is accurate. It will indicate 5 ten-thousandths of an inch per 10 inches. That's 10 arc seconds. So an arc second is just another division of a degree. So you have degrees, which is 1 over 360, which is a full circle. Then you have arc minutes, which is 1 over 60 of a degree, so 1/60th of a degree. And then you have arc seconds, which is 1/60th of an arc minute. So you can see an arc second is a very, very, very tiny number. That's how accurate these levels are. They can show about 10 arc seconds. So when we use these levels to level our machine, we'll be able to level our machine within a couple of thou per foot easily. You cannot do that with a carpenter's level. So you must get some machinist levels. You can get some machinist levels. You can buy one. They're around $300–400. You're going to have to invest in some tools to do this. You may be able to rent some, or if you know somebody, borrow some. Guys don't like borrowing this stuff out. If you drop these, they are junk. So you must be very careful while you're handling these levels. So let's take a look in the machine and see how we're going to level the machine and what we're going to look at. We're at the machine. Got the GoPro set up so that you can actually see the bubble of the level up close. Now when you initially level your machine, A lot of people will put the level on the table and level the machine that way. That is absolutely what you do not want to do. I have the levels on the table because I'm going to show you the final steps in leveling and what we're really after other than just level. What we want to level the machine to is the casting down here on the bottom. So let me jog the Y out of the way here and let's take a look at the casting. So down here you can see our casting. Now this machine is what they call a linear weigh machine. It uses linear rails with linear ball bearings to traverse the slides. The other type of machine that people are familiar with is called a boxed weigh. And what that uses is a steel box, as the name describes, and then they put a material on there that's a friction reducer, and then there's shims in between the saddle, which is this part here, and the boxed weigh. And you adjust those shims to preload it. That's how you take out the play in the system. And then you also adjust those shims to align it. Linear machines are aligned a little differently than a boxed weigh machine. But you can see how these edges are right here? And see how these rails are? Those are the precision machined reference points that you want to use. So you want to put your level across here and then on a rail. If it's a boxed weigh machine, they actually recommend you put the level on the weigh. Now we're using the very bottom of the machine. That is the casting. This machine's actually called a weldment machine. It's a bunch of plates that are welded together. But that's what you want to use to level the machine, because that is the very bottom of the machine. That is the best reference. The reason why level is so important in these machines is because when they build these machines at the factory, the very first thing they do is they level the machine just like you're going to do. What that gives you is a repeatable, measurable datum, a reference point that you can then work up from. So when we do our initial machine level, that's what we want to use. We don't want to use the table. So let me show you why you don't want to use the table. So this machine, it was built in 1994, so it's got some miles on it. You can see there's some wear marks from the vise coming in and out. It's a relatively small table, so most people work in the center, so the center tends to get the most wear. So here's our level. You can see now each one of the red hash marks of the level is 5/10,000ths of an inch. That's 0.0005 inches per 10 inches of distance. So every 10 inches it will measure 5/10,000ths of an inch of rise or fall. So you'll notice the table is slightly out of level. And that's okay. When you level the machine, you want to get the base as close as you can, but then we're going to fine tune it from there based on what we're measuring on the table. So watch what happens when I move this level. I'm just going to move it a couple inches this way. See what happened there? We moved a whole hash mark. So let me move the level this way. We moved 2 hash marks. So you can see these levels are so sensitive that they're going to pick up the little bit of deviation and variations in the surface of the table as it's been worn. So that's why we don't want to use the table. It's not going to give us an accurate measurement. When we use the precision points on the base of the machine, those aren't touched very often. They're hardly ever touched. They're only touched when you need to level the machine, so they don't wear. So they'll always be the same as the day the machine was first built. That's why we want to use those instead. So now I've got two levels here, 90 degrees apart, and I do that just to make this process a little easier because we can check both rotations at the same time while we're running our tests. The next thing we want to do is we want to look for what they call Abbe error, A-B-B-E. And Abbe error is the 3 degrees of motion of rotation. So because we have two axes of movement, we also have two axes of rotation. So as we move our table around, it may be twisting in X, it could be twisting in Y. Now Y, this way, is where the narrow part of the machine is. So the machine is narrow and long. So if you have twist in Y, where the base of the machine is twisting, that's what you want to adjust out with the feet of the machine. You don't want any twist in the machine. As you move X, most machines will have a little bit of twist in X, and that's due to their design. If you look at the design of this Fidel machine and the saddle, as the X slides or the X linears get farther away from the center line, there's less material in the saddle to support them. This table weighs about 400 pounds. So as the table moves back and forth on the X, you'll notice that it's going to start leaning a little bit each way. Now what I mean a little bit, we're talking, 10, 20, 30 arc seconds. That's one of the major differences between a Fidel machine or a Haas machine and, an Akuma or a Mazak or a Mori. Those machines are just built a lot heavier. That's why they cost a lot more. Now those machines, you'll typically see a 10x improvement in that rotational error. They're not going to rotate as much. They're going to be much more stable. You're typically going to get 4 or 5 arc seconds of rotation in those tables. So let's run some of these tests and see what the results are that we're going to get. So we're going to move our level back to the center of the table. Now I'm not going to show the level that's in the Y plane just because it really doesn't move much. This machine is very good in Y. What we're going to look for is twist of the bed, and the way we're going to do that is we're going to watch our level as we move in Y. So let's come all the way towards us in Y. We'll let our level settle out. So we're kind of in between the two minor hash marks there on the end. And then we're going to jog the table all the way the other way. Okay, so you can see our bubble really did not move that much. It moved less than 5/10,000ths of an inch per 10 inches, or less than 10 arc seconds, which is very good for a machine like this. So let's just bring it back one more time. We're at the second hash mark there. So again, we've got almost no rotation or twist while we're moving Y. So our level of our machine is very good. We're only a couple of 10,000ths of an inch per 10 inches off of absolute level. This side of the machine, the right side of the machine, is a little bit higher than the left side of the machine. And the reason why I ended up doing that is when the machine was perfectly level, we had a little bit of twist in the bed as we moved Y. So I tweaked this very front foot on the right side up a little bit to take that twist out, and that's where the machine sat the happiest, and that's where we have no twist. Once we have that measurement, now we want to move in X. So moving in X, that's going to tell us how our saddle is and how the health of the X slides are. So let's move in X. So right now, again, we're right in between the two minor hash marks there. So we'll move, let's move 4 inches. So there's 4 inches, and we'll settle out. Okay, so over 4 inches, we moved maybe a little bit less than a full hash mark. So that's a little less than 10 arc seconds, which is pretty good. Now let's move to 10 inches, which is the full travel of the X in this direction. You can see our bubble moved a significant amount more from going from 4 inches to 10 inches than we did from 0 to 4 inches. Now the reason for that is as the trucks on the linear slides for this machine start getting to the edge of the saddle, they tend to drop off a little bit. So the machine is going to have a natural arc. Now again, remember, we're talking about arc seconds here. You know, a 30 arc seconds is approximately 0.008 degrees, give or take. So we're not talking a lot. So with that amount of angular movement, the center of that radius is probably somewhere, you know, 10, 12 feet below the table of the machine. So it's not a lot. What that error does, though, is as your parts get higher off of the table, you're going to have more uncertainty because the part, this is exaggerated, tends to rock back and forth as the table moves back and forth. If we stay in the center of the table, though, and only use maybe 8 inches of our X, now we've got a lot more accuracy. We've got about 10 arc seconds of movement compared to about 30 arc seconds if we use the whole range of table. That's why these measurements are important. They give you the information you need to know how accurate of a part you can make. If somebody comes up to you and says, hey, you know, I've got a part that's 6 inches and I want you to hold plus or minus 2 thou, you can say, yep, I can do that. But if somebody comes up to you and says, hey, I got a part that's 18 inches and I want you to hold plus or minus 2 thou, you might want to reconsider that, you know, depending on how big the part is. Again, by having these measurements, it gives you information about your machine so that you can judge what kind of parts you can make successfully. Let's take the X all the way the other way. We'll come back to center first. So we're at center. So you can see our bubble didn't change. We've got really good repeatability. We're right in the middle between the two minor hash marks. Let's go 4 inches this way and see where it's at. Oops, I went the same way. Okay, so now we're 4 inches on this side of the table. Okay. Now notice last time the bubble moved this way, and now the bubble's moving this way. So again, we don't have that much issue there. We've only moved, again, maybe about a hash mark or about 10 arc seconds. So let's go 10 inches the full the other way. Okay, so now we went from in between the first two hash marks all the way to the last hash mark. So we moved about 3 divisions there, so that's about 30 arc seconds. So you can see that the table definitely has this arc to it, where, you know, when we're over here, the center's high, and then when we went this way, again, the center's high. And that's typical in a machine like this. again, we're talking very, very small numbers. These are very accurate levels. So this machine is in pretty good shape for, you know, its age and what it's for. So we can hold tolerances easily of a couple of thou with a machine in this shape if we're making, you know, smaller parts in the 6 to 10 inch range. So let's come back to center. And we should see again, we should repeat. Now if we were looking at our other level, we also want to watch that level too, and that will tell us if the table is twisting this way at all as we're moving in X. This table is very good in this axis of rotation, as long as being pretty good in this axis of rotation and Y movement. It only rocks a little bit in this movement. So not only will our levels help us level the machine, but it will give us good information on how good the table is in a rotational plane. You can't measure these very easily any other way than using levels. The ball bar systems and the laser systems will be able to detect this rotational movement as well, but those are very expensive systems that need to be used by professionals that really understand how to use them. You know, simple level, most people know how to use a level. We just need to make sure that we get levels that are accurate enough. When you're setting up your machine, again, it's very important that we level our machines. We first start with leveling the casting at first, then we can move our levels onto the table. And remember, we're not concerned about being absolutely perfectly level. What we're really concerned about is making sure that we take that twisting motion and twisting moment out of the machine. So even though your machine is in dead spot on level, as long as we're not twisting, that's what we're really looking for. And we do that by running the long axis along the base of the machine. After we've adjusted our machine leveling feet and we're happy with how level our machine is, then we can start taking some informational data that tells us how much our table is twisting or rotating around from the mechanics. I hope you enjoyed this video on how to level a machine. The next video that we're going to do is checking the reference of the table to the XY plane. So thanks for watching, and we'll see you in the next one.